All right, so in this video, what we're going to do is everything that you need to know for the EP test about rolling motion. You'll have to excuse me about the sounds outside. I have civeds surrounding my office right now. So here we go, rolling motion. So the first thing we want to do is talk about the three different types of motions that an object can undergo. So first, what we have been dealing with is something called translational motion. And translational motion is when we're considering the motion of the center of mass of an object. So here's the velocity of the center of mass. If an object is only in translational motion, though, like not rolling or anything, that means that every point on that object has the same velocity as the center of mass. No matter what point on the object I speak of, it has the same center of mass because the whole thing is just translating to the side. Next, if we talk about something that is purely in rotational motion, so if I pick the same thing and it is rotating, say, about its center of mass point, so that's where X is. The X is denoting our center of mass, and the triangle is denoting the point about which it's rotating. Therefore, let's say if it's rotating clockwise here, every point on that object is going to have a different velocity based on where it is. And we know that the tangential velocity of any point on the object is going to be equal to omega times r, where omega is the rotational rate of that object, and the r there is how far it is from the axis of rotation, right? So here, we would say that VCOM is equal to 0, right? Here, all these objects have those rotational rates. But when we talk about an object that is rolling, okay, what it's doing is both of these things simultaneously. It is both translating and it is rotating simultaneously. But what we have to realize here for an object that's rolling is that there are two ways that an object can roll. It can roll such that this point of contact slips past the surface, or the point of contact doesn't slip past the surface. So we're going to talk about rolling without slipping for a moment. Now, if you want a more involved conversation about this, you're going to have to go to the textbook. I'm just kind of going through everything you need to know for the AP test. When something is rolling without slipping, what's happening here is every point here is translating, but simultaneously it is also rotating. And you'll notice here this point at the bottom, which we're just going to call point P, the point of contact, as a common thing for this video. Point P, if this thing is rotating clockwise, is actually moving to the left from the tangentially because of its rotation. But if it's simultaneously moving to the right, the whole thing translationally, what happens here is point P, when you're rolling without slipping, is going to actually be at rest, meaning that this object is just instantaneously at rest with respect to the ground such that it doesn't slip. That's going to mean that the center of mass moves at the center of mass velocity, right? Because here there's no velocity component. And this point at the top here, it's going to have both the rotational component and the translational. It's going to be moving with a speed of 2 VCOM. Yes? And so that's what's happening for an object that's rolling without slipping. Now, the nice thing for an object that's rolling without slipping, though, is that that means that this velocity here of point P to the left, because of the rotation, needs to exactly match the center of mass velocity. Meaning, for an object that's rolling without slipping, the velocity of the center of mass is going to equal the rotational rate of the object times capital R. We're going to define capital R to be the distance to the outermost edge. And this is going to be the condition of pure rolling. So if something is in pure rolling, the important idea here is that the rotational motion, omega, is necessarily linked to its translational motion, vcom. If something is rolling with slipping, and this is super important here, so rolling with slipping, that would mean that VCOM is some amount, but the tangential velocity of this point due to the rotation doesn't match this. And it could be either rolling with slipping with backslip or with topspin or backspin, right? Such that here, this point here, VP is not going to equal 0, and therefore VCOM does not equal omega times R. And then depending on whether, if VP is positive, that means that this point is moving like this, so the object's rotating like this, even as the object's translating like that. That means that this thing has backspin, and if VP is negative, that means it has topspin, right? So if to the right is positive, so VP being greater than 0, this has backspin, and if VP is less than 0, that means it has topspin. And these problems are a lot more difficult. We're going to focus right now on something that is rolling without slipping, because in the EP exam, that's where you're going to see the vast majority of your problems. We'll talk a little bit about rolling with slipping in terms of how we could organize that. So if an object is rolling with slipping, that means it is simultaneously rotating and translating. Okay, so let's talk about an object rolling down a hill then. And now we need to know what our object is. We'll say that our object here is a disk. So if it's a disk, we know that I of the center of mass of the disk is 1/2 mr squared. We want to know all of our major moments of inertia. So if this object were to just not be slipping, rather, excuse me, if this object were just to translate, it would translate down the hill like this. So what is it that makes this thing begin to rotate then? Hopefully what you're realizing that it's going to be friction with this point, point P, that's going to cause this object to begin to rotate. And so that's going to become an important point that, actually, let's go one step further. What type of friction? Well, if I'm rolling without slipping, that's going to mean that this point P is not moving relative to the ground instantaneously. That means that I'm going to have static friction at that point, right? So what we're going to say is static friction at the point of contact is what causes changes in the rotational state. Okay, so let's do a free body diagram here. I'm going to have my center of mass point, boom, that's Fg. I'm going to have my normal force coming from the point of contact, and now I need to have static friction. Well, if we think about it here, if we assume that the object is going to rotate about its center of mass, which that's what happens for most normal disks and spheres and hoops, I'm going to need a torque that is clockwise here in order to get this thing to begin rotating. Notice Fg and Fn are not going to cause torques because they act through this the center of rotation. Therefore, static friction must act up the slope in order to make that happen in this case. So that logic is really important in the way we do this. So now if we're going to talk about, well, what happens here, we would do our normal process here. So let's have axes and declarations. I will go positive y, positive x. And so let's go positive x is this way, positive y is that way. Now we need to think about a positive rotational state. And here's where we have to think about what I'm going to call linked declarations. If this thing translates down the hill, this object is going to want to rotate clockwise without slipping. So I need to have that link settled, and you can't mix and match. All right, so let's have some components. So I'm going to have FGY and FGX. Notice I'm drawing FGX from the center of mass of the object now because it matters where that force acts. We know that that is the angle of inclination of the hill. So with that being said, I can do a sum of force equation for that in the x direction. Sum of force in the x is equal to MAX, and I've got FGX minus FS is equal to MAX. And so that's mg sine theta minus Fs is equal to MAX. Now you'll notice I did not plug in mu sub SFN here because I'm not exceeding the maximum value of static friction. I want static friction below that maximum value. I don't want it to slip. If the question were about at what acceleration does it slip, here you would take the limit as Fs approach Fs max and then find that. But that's not what the problem is. So you notice here I don't have enough to solve the problem. So let's go to torque is equal to I alpha. So we're going to do about that center of mass point. The only force that's causing a torque here is the torque due to static friction. And so that's going to equal I, which is of a disk, 1/2 mr squared times alpha. And so here we go. I'm going to have Fs, the lever arm distance here is r, and so it's equal to 1/2 mr squared alpha. Notice I can cancel an r here, and I have an expression for Fs is equal to 1/2 mr alpha. Now, I can put that in here, but notice I'm still going to have two unknowns. Well, the way we resolve that is in the condition of pure rolling, if VCOM is equal to omega r, then the acceleration of the center of mass is going to equal to alpha r. And this x here, this is of the center of mass because we said sum of force equations are talking about the center of mass. Awesome. So that gives me that Fs is equal to 1/2 mr, and then alpha is going to be that Ax over r. Notice my last r goes away. And now I can put this together. mg sine of theta minus, and what do I have here? 1/2 max is equal to max. Okay, so mg sine theta is equal to 3/2 max. And you notice m's cancel. Ax is equal to 2/3 g sine theta. Boom. So now I know the tangential, or the acceleration of that object down the slope. Now, we should note that if this object were just translating, right, just translating with no friction, the only force that would be causing the acceleration is Fgx. And therefore, what would happen if this object was just, all right, cool. If this thing were just translating then, and the only force that was causing it to go down the slope was Fgx, I'd have just mg sine theta is equal to that, and I would end up with g sine theta as the acceleration of the thing down the slope. Notice here, and this is interesting, that the acceleration of the object down the slope when it's rolling is less, meaning that an object just translating down the slope is going to end up going faster at the bottom of the slope than an object that is rolling without slipping. And we're going to have to talk about why. All right, so let me see if I can get that less blurry. All right. So there we go. Therefore, an object just translating down the slope will have a higher acceleration than an object just rotating down the slope. Now, you'll note here that this was for a disk. If I had a hoop here or a sphere here, this would change, which would change these. So just so we have a comparison, because this is a good thing just to have for multiple choice here. So for an object just translating down that slope, that acceleration would be g sine theta. And then if I had the hoop rolling down the slope, we would find out that Ax was equal to 1/2 g sine theta. And if we had this object, which we did the disk, Ax, as we saw here, is 2/3 g sine theta. And if we did the solid sphere, because these are the most common things, Ax would equal 7/10 g sine theta. So what I hope that you see here is that as we go down this line, I is decreasing, and as I decreases, the acceleration increases. Now, that should make sense then, because I is about an inertial term. And the more inertia the system has, because this object not only has inertia now because of its translation, but has a rotational aspect to this inertia, the more inertia that it has, the slower its acceleration is, because the hoop has the highest moment of inertia of all of these. The solid sphere has the lowest, because remember, this is mr squared, this is 1/2 mr squared, and this is 2/5 mr squared, right? So that's a simple and interesting idea there. Now, when that object gets to the flat, it should note then, once it's along the flat, if I look at the free body diagram, I have Fg and Fn. there is no reason why this thing should change its rotation anymore, right? There is no static frictional term. The reason why the static frictional term exists here is because absent there being friction, this object would just translate down the slope because of that FGX term. That FGX term kind of goes away in this. And therefore, as you're rotating, or rather rolling along here, there'd be no change in the rotational motion or the center of mass motion, VCOM. Therefore, Fs would equal, not equal, it would equal 0. Because if Fs existed here as well, not only would this thing change its rotation, it would also have a negative acceleration, start slowing down, and that's simply not happening as you go along. So static friction here for a object rolling without slipping only exists while the rotational motion and the translational motion are changing. All right, cool. So another way that we can conceive of this, so let's go back to this, an object that is rolling without slipping. If it is rolling without slipping, so once again, here's the center of mass, and we know we have the normal force, Fgx, Fgy, static friction. I can also do something really interesting here. For an object rolling without slipping, and only for rolling without slipping, we can say that an object rolling without slipping is mathematically equivalent to an object rotating about the point of contact. Okay? Because if we go back to our earlier picture here, yes, this object here, if I pretend that that object is kind of pinned in place there, that means this object is moving around the edges like that. And those things are mathematically equivalent. Well, what does that allow me to do? Well, that allows me just to do a sum of torques about this new point of contact, I about that point of contact, alpha. Now, once again, if we assume that this thing is a disk, well, what does that give us? Well, now it is Fgx, or the torque due to Fgx, that's causing the rotation. This I here is no longer I, I have to use Parallax's theorem about the point on the edge. So that's 1/2 mr squared plus the shifting factor, which here is mr squared times alpha. And if I look at this, that becomes Fgx times r, because that's what the lever arm distance is for this, would equal 3/2 mr squared alpha. That goes away, right? And then we know that Fgx is mg sine of theta is equal to 3/2 mr alpha, and alpha is still equal to ax over r as long as I'm rotating without slipping. There we go. M's go away, r's go away, and I'm left with, again, that ax is 2/3 g sine theta for this. That's a nice simple way of doing it. So that mathematical collusion for an object that's rolling without slipping is really important. Once again, if it's slipping, all that goes out the window, right? The next thing we have to think about here is we can talk about energy. And so I'm going to revisit this analysis from an energy perspective. So here we go. Let's say I have a hoop in this case, and I have a hoop that's going down this distance, and I want to know, well, how fast is the hoop going when it gets here? So same sort of process. We're going to start with a UG is equal to 0 line. We're going to make that UG is equal to 0 line where the center of mass is initially. Let's say that our hoop is initially distance h above. Well, what form or forms of energy does it have? Well, initially, we know that it has gravitational potential energy. Finally, not only does it have translational kinetic energy, but it's also going to have rotational kinetic energy, right? Because it is both going to be it's both going to be translating and rotating at the bottom. And so this becomes an interesting thing. So is energy conserved now? Is the work done by non-conservative forces 0? And the answer is yes, it is. Because you might say, but there's static friction here at the point. But that static friction is not doing any work because that point of contact doesn't move. So when you roll with slipping, energy is not conserved. That becomes a real big problem. So I can say energy initial is equal to energy final, and a lot of the multiple choice questions are about this. So notice here, I've got that this pot of energy, so to speak, of potential energy is going to get distributed into both the rotational and the translational. So this kind of gels with something we said before. Notice we said when an object is rolling down a hill, it ends up going slower at the end of that hill. Well, here's your explanation. If an object's just translating, all of that energy goes into the translational motion. But if an object is going to roll without slipping down the hill, that same finite pool of energy needs to distribute into these two buckets, so to speak. So what might that look like? Well, mgh is equal to 1/2 mv squared, and that of course is v com, because it's got to be, plus 1/2 I omega squared. So what do I do with this? Well, I know because it's in pure rolling, omega is going to equal v com over r, and then I is going to be equal to whatever it is. In this case, we said it's a hoop, so mr squared, and that's about the center of mass point. So mgh is equal to 1/2 mv com squared plus 1/2 mr squared times v com over r quantity squared. Notice my r squareds are going to go away. I end up with 1/2 mv com squared, 1/2 mv com squared, or mgh is equal to mv com squared. The m's go away, and then v com is equal to the square root of gh. Now, if I just compare that to if I was just translating, v com, like just get rid of this term, would end up being the square root of 2gh, showing that if I just translate down the hill, I'm going faster than if I translate and rotate simultaneously down the hill. Now, an interesting thing on the opposite end of that is if I have an object at the bottom of the hill that's rotating or rolling without slipping, right? So it is omega, it has a v com, and it goes up the hill. Here, initially, my initial energy is kinetic, translational, and rotational. So K Ri plus Ke Ti, and it's going to end up with just gravitational potential energy when it comes to rest at the top. Funny enough, if this thing is rolling without slipping, initially, notice that if it was just translating, like this thing wasn't rotating, just translating along, I would have just this amount of energy going into that. But if it's rolling without slipping, I actually have more total energy to be going at the same speed, and that object would actually make it up to a higher place, right? So it's sort of the opposite thing that what happened when you come down the hill. But the point here is that I can do conservation of energy for an object rolling without slipping. So let's just talk momentarily about rolling with slipping. Terrible problem. So let's say I have an object that's like spinning here, right? Like let's say it has a rotation like this. That means that the point of contact here is trying to slip past the object to the left, meaning here it would actually experience a kinetic friction force, right? And so that kinetic friction force is going to do two things. One, if we look at that, if these are my forces, that kinetic friction force is going to be, so what's happening here? Let me just explain the initial situation. Let's say that I have a bike wheel that I spin really fast and I put down on the ground. So it's already rotating when I put it down on the ground. So notice here, Fk is going to act like the net force in the x direction. So that thing will actually translationally accelerate to the right. But if we think in terms of what the net torque would be, if I'm saying to the right is positive, that means I would want clockwise to be positive because those are linked. This is going to create a negative torque due to kinetic friction. So what's going to happen here is the rotation is going to slow even as the translation speeds up. At some point, though, this slips into rotating without slipping, right? At some point, the rotation slows enough that it doesn't slip past, and that rotation happens when the center of mass velocity equals the r omega. Okay, so those are the main ideas with rotating rolling motion. There are going to be sort of two flavors of problems. The first flavor of problems is with the forces. They're going to want to make sure you know how to draw the free body diagrams. They're going to want to make sure you know how to find alpha, and they're going to want to make sure you know how to find ACOM for various shapes, right? And the second problem is doing energy analysis, looking at the two different things and rolling without slipping, and just making sure that you could say, oh, okay, well, I have translational and rotational here that's going to potential, or whatever the combination is. And the third thing is, what is the distinction between rolling with slipping and rolling without slipping? Rolling without slipping, that's when we have a necessary link between the translation of rotational motion, static friction at the point of contact. Point of contact is instantaneous at rest. Kinetic friction, whether when you're rotating with slipping, you have kinetic friction at the point of contact. The rotation doesn't match the translation, but there are torques and net forces that are happening to bring it into coherence. So that's your quick once over with what's happening with rolling with rolling motion.